In special relativity, there is a thought experiment that is often called the twin paradox. And in this paradox, you have what's called a traveling twin who travels away from the Earth and then comes back to the Earth. And basically, what is usually brought up about the twin paradox is that for the traveling twin, time passes uh, more slowly. So he comes back to Earth and he finds that the people on Earth have aged quite a bit while he hasn't aged as much. And there's usually a lot given to the fact of what he sees when he leaves versus what he returns, but very little is mentioned of what he would actually see if he kept his eyes on the Earth the entire time. And that is what this demonstration is meant to do. The demonstration that I have here is fairly complex. It has several parameters separated by what I'm calling jerk events. A jerk is a change in acceleration. And so I have the jerk events highlighted here in orange. And right here is an event where the traveling twin stops accelerating and travels in a straight line, and then he decelerates from here to here, and then he stops accelerating again here, travels in a straight line. Actually, he's stopped. He's stationary with respect to the Earth at that point. And then he begins accelerating again back towards home, and then over here he stops accelerating, and then he decelerates so that when he arrives back home he has no relative motion. So this is a fairly complex description of what's going on, and what I can do is, what's going on over on this graph is you're looking at it from the twins' perspective. So the point of view stays in the same spot, but I can move it around. But as you see, from his perspective, he is always standing still while he makes the Earth travel away from him. And right here, the image is traveling away at a constant rate. And then at a certain point, he starts decelerating, and the image reaches its full uncontracted length right about here. But then something interesting happens when he begins to decelerate, is that the image actually starts to move away from him. It's very subtle right now. You don't really see it very much here because the velocity is not anywhere near the speed of light. And I did that deliberately because I didn't want to, I wanted to show the more relativistic effects after we went through kind of what you would expect. So now Earth is coming toward him instead of him coming towards the Earth from his point of view. So that is what the point of view of the traveling twin is. Instead of him traveling away from Earth and then going back to Earth, it's more like Earth is going away from him and then Earth is coming back to him. So what I'm going to do now is I'm going to change the acceleration, and the acceleration on here is a little bit strange because this is the region where I would say is the non-relativistic domain, where the time dilation effect is very small because he doesn't get close to the speed of light. But as you get up a little bit, we get to a point where the relativistic effect starts to become more pronounced. When I change the amount of acceleration, I'm not changing the amount of time experienced by the observer. And move it down a little bit. I don't want it to be quite that drastic yet. Okay. Okay, so now what happens, I'm going to come up and change the rate here. So we just watch this a little bit faster. So during the accelerate back phase is what's interesting here, is that the image moves away and then it starts coming back really, really fast before it comes back. So this is a phenomenon called superluminal motion. It's something that happens to images. Even though the object itself is not moving faster than the speed of light, the image appears to come very, very quickly, much faster than the speed of light. And it has to do with the fact that the speed of light, it has to do with the fact that the object is right behind the waves in front of it, so that the waves in front of it kind of get packed up. Now that I've talked about that a little bit, I'm going to change what's displayed over here. I'm going to turn down the red. Okay, or first actually let me talk about the orange line here. Basically, this orange line, I'll zoom in and I'll bring up that slider again. So the events observed on Earth while the twin is accelerating are shown between, okay, actually let me pause it so that I'll use the pause button. Okay, so during this part of the trip, while the twin is accelerating away from Earth, he sees these events here, and then when he reaches a constant speed, he's seeing, wow, wait a second. Those are really close together. Let's zoom in really close so we can see those. Okay, so these are the events that he sees while he's accelerating. Then during the portion of the trip while he's at constant speed, he sees those events highlighted in orange. And then while he's decelerating, he sees these events highlighted in orange. And then we can zoom out because we'll be able to see more, because these other orange sections are much larger. And then while he's at constant speed, while he's stationary with respect to the Earth, he sees those events there that are highlighted in orange. And then when he is accelerating back towards Earth, he sees all these events, which is quite a few more events than before. And then when he reaches a constant speed, he sees these events highlighted in orange. And then finally, he sees those events while he is under deceleration. Now those things are much more drastic over here. Oh, I can't change it that way. So that like I still have them highlighted in orange over there, but they look a little weird because of the slanting going on. What else do I want to show you? Oh, I want to bring up this and this. Okay, so those red lines were based on the jerk events, the events where there were sudden changes in acceleration. But what if we have a signal that is just constant coming from Earth? These is a regularly scheduled broadcast. Broadcast, 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 broadcast. So what's interesting to see is how that looks from the perspective of the twin over here. Let's see, oh yeah, I want to animate it. So those points become very close together there. So let me zoom out a little bit, and I'm gonna make a tick noise with the dots. So we get the first tick takes a while to get there. Tick. The next tick is here. Tick happens while he stopped, and then tick, 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 tick. So you can see that when he's moving away from the Earth, the broadcast is what they call redshifted. It's a Doppler effect. It makes it so the frequency is lower. But then when he's coming towards the Earth very quickly, the ticking gets very fast. And then it slows back down to the normal speed as he decelerates. So those are the tick marks. I'm going to make a couple of comments about a couple of things here. This slider causes those tick marks or the regular even ticking to display or not display. You can change the number of those if you like by editing this line here. Change that to 1 and 19 and divide by 20. And you'll have 20 tick marks, well, actually 19 tick marks instead of 9. So you'll have twice as many ticks. And put that back the way it was, 1 through 9. What else can you do? Oh, you can make those dots bigger and smaller. That's what that slider does there. I just thought it might be, if you wanted to see the different tick marks in different size, it might help to be able to change that on the screen. I've got this so that you can change it at will. How long is the stopover? So you can change how long the twin stays at the location that he's ending, and you can bring it all the way down to 0 if you like. The other parameters down here under parameters, and you can say how long does he accelerate. If he doesn't accelerate it for any time at all, then he stays on Earth. If he accelerates for a very long time, then, well, then he basically reaches the speed of light. But okay, that's a very long period of acceleration. What about this? Tau inertial represents the amount of time that he spends after he does his acceleration. How long does he spend at constant speed? And tau stop does the same thing as the stopover. So those are 3 different parameters that you can change. And what else can you do? Oh, this acceleration, I've set it up. I did not actually find a function that actually like my goal was to try to get a curve that this dot would stay on, and I'm pretty sure that it should be possible in principle. I did not figure out what that curve is mathematically, but what I decided to do was just to create a curve that was asymptotically similar to what this curve is, so that it when the acceleration is 0, then the amount of proper time experienced by the traveling twin is pretty similar to the amount of proper time experienced by the stay-at-home twin. When the acceleration is very high, I need to move this so that it's not in the way. Okay. When the acceleration is very high, you get almost complete, almost all the time passes, well, actually most of the time is passing right there. So you just get the amount of time of the stopover for this. So, and otherwise there's very little proper time during the actual trip. Now, another thing I think I'll point out that I haven't really mentioned is you can move this, just move that POV dot, and it changes. I should probably mention that POV stands for point of view. So the purple dot over here and the purple dot over here are corresponding to each other, if you didn't notice. What else should I mention? That the blue dot corresponds over here and over here, so that the same image being seen by this at this point is the same image as being seen at this point. The only difference is that in this perspective, it's actually at the coordinates that the traveling twin would see it. Some other basics: if you want to change the speed of the animation, you can go over here, click this button, slow it down or speed it up. You can pause the animation with this button here, and I put that up on the top. You might notice that the blue lines, actually, many of them actually go right through the world line here, so it didn't actually stop them. The reason it doesn't, it was actually kind of tricky to calculate these points. It actually calculates, well, it's kind of funny because there is an x1, which is this green curve down here, is right there. Then x2 is that curve right there, a straight line. Then x3 is the slowing down curve right there. x4 is the stopover. x5 is accelerating to the left. x6 is a straight line going to the left. And x7 is accelerating to the right again. So I had to have a way of calculating all those different points. So I ended up kind of shading them according to this function get phase, and the get phase was designed to figure out whether the signal originated in phase 1, phase 2, phase 3, phase 4, phase 5, phase 6, or phase 7. So what I actually had to do was calculate every intersection of all of those blue lines with that red curve, every intersection of those blue lines with that red line, every intersection of those blue lines with that red curve, every intersection of those blue lines with that red line. Anyway, after I calculated all of those, I decided that what I would do is simply shade the dots according to which phase the origin of the blue line was in. whether it came from phase 1, phase 2, phase 3, phase 4, phase 5, phase 6, or phase 7. And so that kind of gives you an idea of how complicated it was to find the locations of these well, 10 dots here, which I can turn into 19 dots by doing this, or 100 dots by doing that. That looks a little intense. Anyway, once I have those dots, then the main thing I wanted to get out of those dots was the idea of how much the blue shift happens. There is a great increase in the frequency based on where those dots are located. And yeah, you get that an extreme blue shift, and you have a large number of consecutive images because you have the superluminal motion. Everything you're observing is an object that's moving towards you. By all appearances, it would look like it's coming at you at faster than the speed of light, and also it would look like everything was happening in a fast forward, and time was passing very, very quickly in that image. So I think that's about where I'm going to wrap this up. I'm going to put a link to this demo down in the description, and put a link to the YouTube video in the comment section down below. All right, that'll be great. Have a great day.